Well, now that we have our projectiles code set up, let's have a little fun with it. Let's make some projectiles games. The first thing I'm going to do in order to turn this into a game is give you an opportunity at the beginning of the code to specify a launch speed and a launch angle, because we've been specifying the initial velocity based on its x component and y component. Kinesthetically, it makes a little more sense to think about how fast you're throwing a projectile and at what angle you are throwing it. So what I've done here is set up launch speed and launch angle. This will be in meters per second, and this will be in degrees. So what we're going to do with those two is place them into the ball.velocity vector. So instead of having just our x component and y component, for our x component, we're going to have cosine of the launch angle. For y component, we'll have sine of the launch angle, and then we'll multiply the whole thing by the launch speed. So that launch speed is going to propagate into each of these components. VPython knows how to distribute a scalar multiplier into a vector's components. And you notice we also need to convert that launch angle into degrees here, but we're trained to think in, excuse me, did I say degrees? I meant radians. We also have to convert the launch angle into radians here. You and I are probably trained to think in terms of degrees, so we'll just give it as degrees here. So when I run this now, what I'm specifying is how fast does it launch with and at what angle does it launch with. So what kind of games are we thinking about? Well, first let's try basketball. Right? Let's try getting this thing into a basket. So what I'm going to do is set up a basket here. I can set up a ring in VPython. Oh, there's my ring there. I need that to be oriented a little bit differently, so we'll give this thing an axis that points, I think, upward we want, 0, 1, 0. Cool, cool. There's the basket there. We'll want to, let's see, I think we want to make this thing's radius a little bit different. Let's try giving it a radius of 2. Okay, yeah, so that changes its radius going this way. We can also reduce the ring's thickness a little bit. So let's make that maybe a 0.1. It should change that inner radius. Yeah, something like that. And let's make it a different color compared to the ball here. So let's go color equals color dot. Let's see, let's make the basketball here red. And let's make this thing have a color of, you want to say green? There we go. So we're trying to get the basketball into the hoop. So I'm clearly not doing that yet. So what I would do here would be to adjust the launch speed and the launch angle until I make it in. So let's try tripling the launch speed. Oh, went too far. So if one was too far and one was too short, we'll go in the middle. Oh, perfect. On the third try, not bad. I mean, I made the basket plenty wide, so you could make the basket a little bit narrower. But it would be nice if the computer could give me any feedback about this game, right? Because I would like it to be able to tell me, did I get the basket or did I not make the basket? So what we're going to do is set up a conditional to check for whether we scored. Scored equals false. Because we start out, we have not scored yet, right? We have not made it into the basket yet. So what we can do, we can now have the loop run while the ball is above the floor and while we have not scored. And so right now that's not going to change anything because I've set score to be false. I'm not updating it. But now I would like to check for whether I have scored. Check for whether we made a basket. So how can I do this? Well, the ring has a position, right? Its position is currently at the origin. So let's try setting basket.pos equal vector. Let's start with it at the origin 0, 0, 0, right? It starts out there, but I want to know if the ball makes it within one ring radius of the center there. Well, let's think about how we might do that. So in order to do that, this thing is oriented in the XZ plane, right? Because my Y goes this way. So I care about whether their Y values are about the same, right? So the first thing let's do is ask, are their Y values close. Now, I'm saying close here because with these things being decimals like this, you're never going to get them equal to each other because there's always going to be some digit out there where they differ. But I just want it to be close enough, right? So let's suppose we make this if we want to check for whether their y values are about the same. So let's say if ball.pos.y minus the ring, the basket.pos.y is less than some amount. Let's call it the tolerance. So we'll set tolerance to be a small value, say 0.01. That should be fine. Now the thing is, the ball might be above the basket. Let's see, the ball is going to come in above the basket. So ball.pos.y minus basket.pos.y is always going to give me a positive number because I've got a greater thing minus a lesser thing. So that is fine. Anytime you're subtracting, you just want to think about whether the sign is positive or negative. If you're ever in doubt, just put an absolute value around it because that'll take care of both cases. Okay, so we check for are their y values close. So if so, we're going to move on to the next thing. So the way the structure works, we're checking for if this condition is true. And if it is true, we move to this next piece. If it's not true, we skip it. So we're only doing this if this part is true. So now we need to check for is the ball's position within the ring's radius. And so for this, we're going to check its x and its z value. So let's do it this way. So if I want to get the separation between those, the separation vector is going to be ball.pos minus basket.pos. Anytime you want the distance between two things, just take their two position vectors and subtract those. And I can make this into a magnitude here. Let's see. In principle, this is checking x and y and z, which is fine because we've already established that the y value is small, right? So that's not going to make a difference here. So this should be fine. I was thinking I would have to do the to look at the x and z values separately, but I can actually get away with just doing their separation there. And so now let's check for whether this is within the ring's radius. So if separation is less than, what did we call this thing? It's called the radius, so basket.radius. And you notice this is already a positive number because magnitude always going to be positive, or 0 if we get really, really close. Is less than the basket radius. Then we have made the basket, right? We have scored. So scored is going to equal true in that case. So notice I'm checking on these two conditions. First I'm checking this one, then I'm checking this one. I could combine those into a single line, but I think for introductory purposes it's helpful to kind of separate those. If neither of those is true, then I do need to maintain scored as false, but that's going to be maintained. It's already equal to false. I don't need to keep it at false. I don't need to tell it to stay false. It's going to stay as false there. And so what we'll do here is, let's see, so we'll put in print score. And let's give it a little banner here of equal signs just so it looks really cool. All right, let's see if that works. I might need to move the ring up a little bit. And okay, we did get a score here. Isn't that cool? I don't think I actually need this info here. I'm going to comment it out because I don't think I need it. But now I've got the code able to tell me whether we scored here. Let's try a little bit different challenge. Let's suppose I move the basket up, right? So let's suppose I move it up 1 meter. Well, no, I'm not. Oh dear. What happened here? Oh, you know what? Okay, I do need an absolute value around this because ball.pos.y is negative. And so I've got negative minus number. Yeah, that's going to be less than this positive tolerance. Okay, so I do need absolute value around here. This is why you always test things before you deploy it, right? Before you say it's done, you always test these things. I did not get a score there, right? So let's have it print here. If not scored, print no score, ... frowny face. Boop, yeah, no score there. So I did not score there. So now I can start making adjustments to this thing, right? I could... Maybe I don't want to increase the launch speed. Maybe I want to increase the launch angle. Let's make that 25 degrees. So launch. Oh, just over. So again, let's split the difference. Go with 20. And there we go. And you notice it stops as soon as I get in the basket. It doesn't have to wait to get to the ground because it's tracking. It's going to keep repeating as long as both of these are true. So if either of them is false, it's going to exit the loop. So we just get a nice photo finish there of our score. Now, in principle, I need to tweak this just a little more, right? Because if I decrease the launch speed just a little bit, let me see if I can get this perfectly here. No score there. If I get this at just the right launch speed, something interesting is going to happen. Did you notice how it passed through the ring there? Let's get this just a little bit faster. So, nope, that one did not score either. Let's go up to 9.8. What you notice is it's saying I got a score, but if I look at this thing, I really should have ricocheted off of the ring there. I should have ricocheted off the basket, right? That would have bounced off there. So my model's not quite perfect yet, and maybe in a future version we'll implement a rebound off of there. But that requires us to learn a little bit about momentum and kinetic energy. We'll save that for a future project. But the cool thing is now I've got a system where it can tell me whether I have made it in the basket. And so what I can do is present this as a challenge to students, right? I can change the position of the basket, right? Maybe I move it up more, and maybe I move it over to the right some. And students have to figure out what the appropriate launch speed and launch angle are. Now you can solve this on paper, right? I could have my students do this analytically. But I am kind of more interested in seeing them, work this out in the code, kind of doing this like an experiment. Now, this case here brings up an interesting question. What happens if it goes up through the ring? Yeah, so right there it went up through the ring. That doesn't count as a score, right? So I need to check for one more thing. I need the ball to be coming down. So let's put in one more check before we go for the day. Let's put in if the velocity is going up. So that's the y component. So that's ball.velocity.y. So it's the ball's velocity's y component is greater than, should we count it at 0? I don't think we should count it at 0. I think we need it to be, not greater than 0, less than 0, right? If it's coming from above, then it is a negative velocity going down. If the ball.velocity.y is less than 0, then we get a score. Okay, let's repeat the same trial. We should get no score this time. Oh, that's weird. Oh, I didn't tab over the print score. There we go. There are physics errors and then there are computing errors. So this one just sails right on through, no score, because it did not make it going down through the basket.